In this lightning talk session is from Chun Yeung from Columbia University. We'll be talking about a non-asymptotic perspective on mean field control.
Thanks a lot, Dan, for the introduction and for organizing the workshop along with Kavita and the local organizers. The title of my talk is A Non-Asymptotic Approach to Mean Field Control. And it is part of the results of a working paper titled Mean Field Approximation via Log Concavity, joined with my advisor, Dan, and Sumit Mukherjee. Here's a brief outline for the talk. I'm going to start with the motivating question and then discuss its connection with mean field control. After that, I will state our main results. And then lastly, I will give some ideas of the proof. Let's start with the motivating question. Consider a large population of players, which we index by I from 1 to n. Player I chooses a Markovian control alpha I, driving the stochastic differential equation dxit equals alpha I dt plus dbit. The control of player I is allowed to depend on time t, as well as xt, which is a vector denoting the state of all n players. And these players cooperate to maximize the expected reward gxt minus a half of the quadratic running cost, of the average of the quadratic running cost. And we call the optimal value v. Now, this optimal control problem is well studied, and the optimal control alpha star has this log derivative form over here, and it's commonly known as the Fell matrix. Now observe that the control of player I in general depends on the state of all n players. So the dimension of the optimal control for each player increases with n. Therefore, a natural question is, can we approximate this alpha star by a control which is much more low dimensional? And by that, I mean a control of the form alpha hat, which depends on time t, and xi, which is player I's own state, and not the states of the other players. And we call a control of such form a decentralized control. And if we formulate the decentralized control problem, which has the same objective as the original one, but we restrict the class of admissible controls to just decentralized controls now, then clearly the optimal value in this case, v hat, can be no better than v. But when is v hat close to v? That's the motivating question. This question turns out to be well understood in the literature of mean field control when G has the following symmetric form. So Gx is capital G of the empirical measure of the states of the n players. In this case, the n player problem takes the following form. And it is commonly argued that as n goes to infinity, the value for the n player problem converges to a limiting mean field control problem. It is a one-dimensional stochastic control problem obtained from the n player one by replacing the empirical measure with the law of the control diffusion at time capital T. And it can be thought of as a problem faced by a representative player among n players when n is large. And we can use the optimal control alpha star from this limiting mean field control problem to construct a decentralized control for the original n player problem, just by giving all the n players the alpha star from the mean field control problem. And this decentralized control can be shown to be approximately optimal for large n. Our main result is the following non-asymptotic bound on the approximation error achieved by decentralized controls, which goes beyond the previous symmetric setting. Precisely, if we let G the terminal reward function to be C2 and concave, then the difference between the optimal values of the original and the n player on the decentralized control problems are bounded by this error term over here on the right. It is proportional to n times the supremum of the sum of the cross derivatives of G. And so this implies that if this error term is of the order of 1, then decentralized controls are approximately optimal when n is large. I would like to emphasize that in the error term here, only the cross derivatives are included and not the diagonal derivatives. As an example, let us go back to the symmetric setting we have discussed before. So Gx is a function capital G of the empirical measure. If capital G is more of a concave and twice continuously differentiable in the sense of Lyons, then the cross derivatives of G can be expressed in terms of the second L derivative. And if this second L derivative is bounded, then the O1 condition we have seen previously in the main theorem is satisfied. So decentralized controls are approximately optimal when n is large. Again, the fact that only the cross derivatives of G are included in the error term in the main theorem is crucial for this to work. Otherwise, there would be some other terms coming up from the diagonal derivatives, which cannot be expressed in terms of the second L derivative. So for the rest of the talk, I'm going to try to explain the ideas behind the proof. The proof consists of two main steps. So the first one is the following representations of the two optimal values V and V hat. The first equality for V essentially says that the stochastic control problem can be reduced to just the optimization of the terminal law of the control diffusions at time capital T. This is essentially a well-known consequence of Berzano's theorem. And the second equality here is a consequence of the Gibbs variational principle, which says that the supremum is the same as the log partition function on the right. And for the decentralized control problem, we have a similar equality for V hat, but now the supremum is taken over all product measures only, because decentralized controls necessarily lead to diffusions which evolve independently of one another. I would like to make a slight digression here by mentioning that equation 1 actually leads to a semi-explicit characterization of the optimal decentralized control. Specifically, if you let Q star denote the optimizer over here, then the optimal state process is just the Brownian bridge with terminal law Q star. And the optimal decentralized control is the associated Fermat drift, which has this log derivative form here. Optimal decentralized control is obtained without reference to any mean field limits. Going back to the proof, the second main step, which is the most novel part of the proof, is the following mean field approximation bound, which bounds the log partition function and its mean field approximation, which is the same as V and V hat, by this error term over here that we have seen before, which involves the cross derivatives of this mean field approximation bound can be proven via the Gibbs variational principle and a couple of well-known functional inequalities, namely the log Sobolev and the Poincaré inequalities. Finally, I would like to end by mentioning that this mean field approximation bound holds for much more general Gibbs measures than the one over on the top. In particular, the Gaussian reference measure can be replaced by any C2 and strongly log concave product measure. Moreover, much more is known about the mean field optimizer here on the top. It is in fact unique, strongly log concave, and has a semi-explicit form in terms of a fixed point equation. And leveraging this more general mean field approximation bound, we have two more applications concerning continuous Gibbs measures on large graphs, as well as high-dimensional Bayesian linear regression. With that, I would like to end my talk here. Thank you very much for your attention.
And we have time for one question once again.
Can you compare the controls, the feedback that you have in this way with the one you get decentralized, and can you compare this with the optimal one from the original problem? So you compare the values, can you compare the controls? This is my question.
Thanks for the question. I think you mean this alpha hat star and the one we begin with, this one, alpha star. So, so this one, of course, I think the main difference is that this one depends on the state of all n players, and the ones alpha hats depends only on alpha hats I depends only on xi. So the player I for the player I only sees its own state, and they both have a similar form, which is this log derivative form over here. But other than that, then that's I think all I can say about this. I think the main complexity lies in this Q star term over here. Yes, so we do not have an explicit form for it. We only have a semi-explicit form for this in terms of a fixed point equation.
Thanks for your talk. A quick question. So this bound that you have, this non-asymptotic bound on the Gibbs measures, it looks like, or on G actually, the GIJ, this cross terms, is very reminiscent of this complexity bound that you have when, Chatterjee Dembo, when you're looking at these Gibbs measures. Can you say what the connection is with that? Because they're doing the same thing, looking at Gibbs measures and their mean field approximations.
Thanks, Vivida, for the question.
The decentralized control bound.
And specifically, would you mind repeating?
Does this relate in any way to the complexity bound of Chatterjee Dembo and nonlinear Dodge deviations? Because it's coming from the same sort of comparing Gibbs measures.
Exactly.
Approximations.
Sure. Yeah, thanks for your question. So the Chatterjee and Denbo bound involves covering numbers, and the main difference, the main difference is that this one do not have a covering number form, just a supremum of the off-diagonal derivatives of G. So in this case, this is a bit more tractable, I guess. Right. Other than that, then but they do not require any smoothness assumption. Here we require G to be C2 and concave. Actually, not in the original Chatterjee and Denbo paper, they do require a bit of smoothness condition. But yeah, I guess the main difference is that this is not formulated in terms of covering numbers. I guess is more transparent in a sense.
Yeah, there have been various extensions of the Chatterjee Denbo.
Right, yeah.
Don't require those numbers.
Right,
Okay, thank you very much.
Yeah.
We can talk offline. I don't want to. Thank you for your nice talk.
Thank you.
Okay, then let's thank everyone again.